Hello, welcome to everyone in this video. This is our lecture number 4 of quantum mechanics theoretical part. We discuss three lecture on theoretical part of quantum mechanics and another playlist for the solution of the problem asked in the quantum mechanics of different books. Okay, so if you wants to watch the previous lecture and others part of the quantum mechanical solution or the others part of physics related theoretical and problem solution, you can go through the description box, link are given there. Okay, or you can go through the channel, that is the physics by Laxmikanta sir. You can get the playlist, different playlist for different part of physics related video. Okay, so if you want, you can go through the description box. This is the syllabus for quantum mechanics third semester. This portion, that is the black body radiation, this portion, and the photoelectric effect, Compton scattering, this part we already discussed in the previous three lectures. This portion already discussed in previous three portion. In this lecture we want to discuss, that is the Davisson-Germer experiment, de Broglie wavelength. De Broglie hypothesis already discussed. De Broglie wavelength, matter wave, wave particle duality, wave description of particle by wave packet, group and phase velocity and relation between them, probability interpretation, normalized wave function as a probability amplitude. So this is the our topic to was to discuss in this lecture. Okay, so let's start, and this will be the covered in the upcoming session also. So let's start. The first start at the Davisson-Germer experiment. This is the experiment where actually prove the relation of the de Broglie hypothesis. What will be the de Broglie hypothesis? De Broglie hypothesis, Broglie hypothesis says the relation hypothesis. De Broglie hypothesis says, okay, this is written here. No. De Broglie hypothesis says this lambda equals to h by p. H is the Planck constant, and p is the linear momentum, and lambda is the wavelength. Okay. So this is the relation, that is lambda equal to h by p. H is the Planck constant, p is the linear momentum, and lambda is the wavelength. Clear? So this relation actually verified by this experiment, that is the Davisson-Germer experiment, actually proved this relation. Which relation says the relationship between the particle nature, linear momentum is the nature, particle nature, and the wavelength is the wave nature. So this is the relation between the wave nature and the particle nature, and this relation described or established or verified through this Davisson-Germer experiment. You can see this is the experimental setup. This is a filament, and this is the electron gun from where the electron is ejected due to heating. This filament actually heat up this material and then ejected the electron. Okay, so this as a electron gun, and these are the collimator, which is collimated because these are the scattered in the different direction. For uniform direction, this collimator actually used, and they collimated along to earth's direction, and it increased also the speed of the electron by this applying the potential difference light here, and it's collide with this target. This is a crystal target from where electron is this, and it's scattered along that direction. And this is a detector. This is a detector where actually the detector, this actually connected with this monitor like that. So this is a detector which can detect the electron. So if you change this angle, you will be get the different electron intensity, because it's collect the electron and flow through this current. There is a circuit where measure the current. So if you change this angle theta, you will be get the different current through this, that is the intensity. So if you plot this intensity versus, this is the intensity, r is nothing but the intensity, this is r, this is the intensity versus theta. If you polar graph, these all are the polar graphs, these all are the polar graphs. polar graphs, that is r theta. Here r is the intensity and theta is the angle. Intensity and theta is the angle, or you can say theta prime in here, no problem, theta prime. Okay, so if you plot at when this applied voltage is 40 volt, if you plot this intensity versus theta, if you change this angle theta is 0, this becomes infinity. At a certain theta, this is like here with increasing theta, like there at theta 90 this will be 0. Okay, theta 90 this is 0. Okay, so this is the graph. I think you clear about this. At 30 degree this is the value of intensity. At 20 degree this is the value of we reduce this. So this is the angle 30, 40, 50 with increasing, because this angle taken from y-axis. Okay, so this r theta represented like that at 40 volt. When the voltage is 48, there is a hump arises, and this hump is maximum at 54 volt. 54 volt, this hump is maximum, and this angle is 50 degree. Okay, so this is the experimental result which obtained the Davisson-Germer experiment. Now comes into the theoretical part. You know, from the solid state physics, the Bax's law says that n lambda prime equal to 2d cos theta. N lambda prime equals to 2d cos theta, where n is the order number. Order number 1, 2, 3, 4, like that. Okay, n 1, 2, 3, 4, like that. So this is the Bragg's law, and from the Snell's law you can see here that is the mu is the refractive index. There mu is the refractive index. This mu is nothing but the refractive index. This mu is nothing but the refractive index, that is c by v, and this can be written as nu lambda by nu lambda prime. So this is lambda by lambda prime, and you can see that is this nu equals to sin theta prime by sin 2 theta, sin theta prime by sin 2 theta. This is the angle of incident. You can see this theta. So this is the incident and this is the refracted. That's why this is sin theta prime by 2 theta. Now comes into that Bragg's law, 2t sin theta, and you can see this angle theta. This angle theta means this angle theta, that is this angle theta. Okay, this angle theta means this angle theta, because this theta and this becomes 90, and this and that angle also 90. So if this angle theta, so this angle also theta. From here you can see this is theta and this is small d, this is capital D. So sin theta equals to perpendicular by hypotenuse. Okay, so small d is nothing but capital D into sin theta. Put this value capital D into sin theta, you will be get 2 sin theta cos theta, that is sin 2 theta. So n lambda prime equal to like this, and sin 2 theta, you can see sin 2 theta from here you can see that is the lambda prime by lambda sin theta prime. So lambda prime by lambda sin theta prime, lambda prime cancel out, and this n lambda equal to d sin theta prime. Okay, so this is the obtained from this using the Bragg's law, where we will be get from solid state physics. So from Davisson-Germer experiment, we got at angle 50 degree. At angle 50 degree, this is the maximum value. So put this angle 50 degree, and this d value is given from the solid state physics, that is the separation between this atom. You will be get the value of lambda. And from the de Broglie hypothesis, that is lambda equals to h by p, and p is nothing but 2m E energy, because E equal to P square by 2m. So this energy equals to 2m EB, energy in terms of voltage EB. So you'll be get that is 12.26 by root V in Angstrom. This is the formula which is obtained from de Broglie hypothesis. So this is from Davisson-Germer experiment, and this is from de Broglie hypothesis, theoretical, and this is experimental, right? So this is experimental result, and this is theoretical. So this experimental and theoretical result both are nearly satisfy. You can see how close they are. So this de Broglie hypothesis actually verified through this Davisson-Germer experiment. Clear? Go to the next part, that is the dual nature. We already discussed in the first part and something about the dual nature, why the quantum mechanics differ from the classical mechanics. We discussed in the lecture 1. You can see that, and from where we already saying this de Broglie hypothesis, that is lambda equal to h by p. H is the Planck constant, p is the linear momentum. So this is the particle nature, this is the wave nature. So any particle consists the wave. So wave and particle are the dual nature of any particle. Okay, so any particle associated with wave. So if you just change this formula in the other form, you can see that p equals to h by lambda. And so if you take 2 pi here, so h by 2 pi taken as h cross, this is nothing but reduced Planck constant. H is the Planck constant. If you divide it by 2 pi, you will be get reduced Planck constant, which is h cross. And 2 pi by lambda is nothing but k. K is the wave number. So p equals to h cross k. Similarly, energy equals to h nu. So h by 2 pi and 2 pi nu. H by 2 pi h cross. 2 pi nu is the omega. Omega is the angular frequency and nu is the frequency. So in relativistic case, you can see that is lambda equal to h by p, p equals to mv, and put this value m is m naught by root under 1 minus v square by c square. So if you expand in the binomial expansion, that is 1 minus x whole to the power half, so this will be the binomial expansion. I think you understand the binomial expansion, that is 1 plus x whole to the power n equals to 1 plus nx plus n into n minus 1 by 2 factorial x square plus n into n minus 1 n minus 2 3 factorial x square, so on. This is the binomial expansion. So using this binomial expansion, you can see here, and if you neglected the higher order, that because v is very less than through c, that is the velocity of the particle is very lower than the velocity of the light in free space, then you can see this is the formula for the lambda for relativistic case. Okay. Now comes into the phase velocity and group velocity. What will be the phase velocity and group velocity? Phase velocity actually, when a particle associated wave, suppose the particle associated wave, and this wave can be a single wave, that is the phase single wave velocity is the phase velocity, and when the more wave becomes a single, that is a superposition of wave, you will be get the group velocity. Simple. So group velocity is the superposition of waves, and phase velocity is the velocity of singular. Okay. Now we want to derive the relation between phase velocity and group velocity. Take two equation of two wave. These two waves have the equation, sinusoidal equation, that is y equals to a sin k is minus omega t, or you can see sin 2 pi x by lambda minus vt, any form, and y prime, that is the another wave represented by like that. So if you superimpose these two equation, you will be get y plus y prime. So if you added these two things, you will be get a sin a plus sin b is formula, that is the 2 sin a plus b by 2 and cos a minus b by 2. So just taking this formula. So you can see that is the angular frequency is like that, and this is the propagation vector, and the velocity of the phase velocity will be like that, that is omega by k, and the group velocity will be like that. So phase velocity is omega by k and group velocity is the d omega by dk. So if you want to find out the relation between phase velocity and group velocity, you will take, so this is the phase velocity omega by k and group velocity d omega by dk. So du dk, that is 1 by k d omega, just taking the derivative with respect to k here, you will be get 1 by k d omega dk minus 1 by k square omega. So d omega dk is nothing but ug group velocity, and omega by k is taken as the u, so this is ug minus u by k. So finally you will be get k into du dk equals to ug minus u. So ug is nothing but u plus k into du dk. So du dk change into the du d lambda like that. Lambda k equals to 2 pi by lambda, so lambda equals to 2 pi by k. So d lambda by dk is nothing but minus 1 by k squared into 2 pi. So if you put this value, d lambda by 2 dk is here and du by d lambda is like that. So you just put this value, that is k equals to 2 pi by lambda, you will be get this relation. Okay, so just putting this value, you will be get this relation ug equals to u minus lambda du d lambda. So this is the relation between this is the relation between this group velocity and phase velocity. Ug is the group velocity and u is the phase velocity. Clear? Now comes into the point that is a relativistic case. So phase velocity equals to nil lambda, that is y by omega by k, and in the special theory of relativity, you know the E equal to mc square. M is m naught by root under 1 minus v square by c square. So and you know E equal to h nu, that is h cross omega, and similarly P, that is the momentum, equals to mv, so m equals to either, and you know this momentum equals to a h by lambda, change into like that. Previously we just derived this two thing. So if you take this their ratio E by P, you can see this ratio provided you c square by v, and from here omega by k. So the phase velocity, that is omega by k, is nothing but c square by v. So u into v equal to c square, and from de Broglie hypothesis, this velocity is nothing but the group velocity, that is the velocity of the particle, actually the superposition of wave, and this is the group velocity. So u into ug, that is the phase velocity into group velocity, must be equal to the c square. This is the relation between the group velocity and phase velocity in terms of c square. Okay, now taking this energy equation from the relativity, that is E square equal to p square c square plus m naught square c to the power 4, E equals to h cross omega and p equals to h cross k. So take this, and you know u equals to omega by k, u equals to, you know u equals to omega by k. So omega equals to uk, omega equals to uk, put here omega equals to uk somehow, and you will be get these things divided by h cross square k square square, you will be get these things. So taking the c is a constant, you will be get this one. So you can see there is a plus sign, so this u must be greater than c, u must be greater than c, that is the phase velocity is the greater than the speed of the light in free space. You know, previously we just obtained the u into ug equals to c square, that is phase velocity into group velocity to c square, and phase velocity is greater than c, must show since this is greater than c, so group velocity must be less than c, because their product is c square. So group velocity always less than the speed of the light in free space, that is less than c, and phase velocity can be greater than c. Okay, so this all about the phase velocity and group velocity. Now comes into the probability interpretation. Actually, when a particle situated at that point, if you classically you can say this is the position x equal to 5. Okay, but in quantum mechanically you can say about the particular position, you can say region. So this is the region, you can say the probability, that probability is maximum at that point. If this at x equal to 5, suppose this is x equal to 5 at a particular time, this can be say this is a maximum probability. You cannot say quantum mechanically this is the position of the particle, you can say this is the probabilistic position of this particle. That is the maximum probability is presenting here, but it can present at here also with the lower probability. Okay, so in quantum mechanics you can represent the position of a particle by using a probabilistic function, that is the psi function will be like that, and this probability can be calculated out this psi star psi into dx, that is the complex conjugate, psi star is the complex conjugate into this. And normalized wave function is nothing but when the probability, total probability is 1, then this function is taken as the normalized wave function. You can denote it by n here, denoted by n here. So this psi n is the normalized wave function, normalized wave function. This psi n is the normalized wave function. Okay, so I think clear all about this thing which you want to discuss. If there is any doubt, you must comment in the comment box. This is all about me, and this is my contact detail, you can connect with me with this Telegram channel, and this is my online platform, and this is my YouTube channel details. Go to this channel, you will get different physics related videos, some mathematics. Like this session, if you learn something from this session, share this video to your friends, either he or she also get benefit from this video. Subscribe this channel if you new in this channel. Those already subscribed, thanks for subscription. Press the bell icon to get notification of upcoming video. So take care, we'll meet in the next video as soon as possible. Thank you.